Today I am going to cover Chapter 14, Acids and Bases. First of all, I want to think about some examples of acids and bases around us. There are many substances that are around us that are acidic or basic, so just think about a few examples. These are some of the examples I can provide to you. So take a look at these, and as you can tell, there are many common acids and bases around our everyday life. Okay, I would like to actually review the acid nomenclature before we can move on. First of all, to be an acid, you must have a hydrogen as the first element of the chemical formula. Number of hydrogens depend on the anion's charge. So if you have -1 anion charge, and then you just need one hydrogen, because every hydrogen is a +1 charge. Naming acid. If your anion of the acid ends with IDE, ide, then you'll have to simply have a prefix and then blah blah ic acid. The blah blah part is going to basically become your name of the anion. And then anion ending with ATE. And if you have anion ending with ATE, then you are going to name this ic acid. And if you have an anion ending with ITE, then you're going to name this one blah blah us acid. So you have to basically know these three rules and the subscripts and subscript. I'm sorry, not the subscript. And suffix for each of these are named for. Here, we're going to take a look at the first one. You have HCl. Z is starting with hydrogen, so this is definitely an acid. You have hydrogen with chlorine, which is chloride, and since NIDE, you're going to name this one the first rule, which is going to be chloric acid. Next one is nitrate, 8N. NO3 is basically a nitrate ending in ATE, so you're going to be using the second rule, calling this one just nitric acid. The third one, again, you have just Br single element, bromide, so you're going to call this one hydrobromic acid. Next one is a sulfite. Note that there are two hydrogens. That's because sulfite has -2 charge. So ending in IT, one is going to have sulfurous acid. Next one is C2H3O2, which is acetate, ending in ATE. So you're going to call this one acetic acid. And the pure sulfur, which is a sulfide, called hydrosulfuric acid. The last one is a ClO4. ClO4 has a name called perchlorate. So it's ending in ATE. Make this one perchloric acid. Okay, I hope you guys are a little bit better prepared for the acid and base lecture. Now we are going to move on with the properties of acid and bases. First of all, acid tastes sour. Acid react with metal to form hydrogen gas. And typically, I'll show you guys a demonstration of a grip that I put into the hydrochloric acid and show you guys how acid react with the metal and form hydrogen gas. Instead, I'm going to share you guys a YouTube link, and this YouTube link is basically doing what I was going to actually do in the class. That this video will even actually show you testing the hydrogen gas, which we have done already in our previous gas law lab. So how the creation of hydrochloric acid affect the reaction? Well, a higher concentration of hydrochloric acid means that you have a more abundant hydrogen cations available. And more available means that which will drive the reaction go faster. Bases. The bases taste bitter already because some of you guys had to wash your mouth with the soup as a kid. And you probably have a bad experience about it because it probably tastes pretty bad, right? It's bitter. That's because all the cleaning supplies, which are all basic, right, are going to taste bitter. And they're slippery to touch, as you can tell, soap, shampoo, conditioner, all of them are. And bases and the metals do not react like acids do. What is the pH scale? The pH scale is related to the concentration of hydrogen ions, which determines how acidic or basic a solution is. The pH of a solution is a negative logarithm of the hydrogen ion concentration. This can be actually mathematically calculated using this formula. pH is equivalent to negative log of concentration of hydrogen. Remember, this bracket, right, represents the concentration, which is usually measured in molarity. So if a pH mathematically determined to be below 7, then it's called acidic. It's exactly 7 is neutral, like water, and it's called basic if it's above 7. Here are some of the known pH. Our pH levels are like close to 0. And it's possible to have negative pH levels too. Some of the really concentrated hydrochloric acid is going to have a negative pH. And it goes all the way up to the drain cleaner. And these have a very high pH level because it's very basic. And as you can tell, the water is at a pH 7, which is neutral. Litmus paper. Litmus and litmus paper is one of the dyes commonly used to distinguish solutions of acids and bases. Acidic solution contains more hydrogen ions than hydroxide ions. So when you're saying something is acidic, it means that there are more hydrogen ions than hydroxide. Basic solution is the opposite. Contains more hydroxide ions. So any acid will cause the blue litmus paper to turn red. And the aqueous solution of a basis will cause a red litmus paper to turn blue. So a lot of you guys probably use a litmus paper in biology class. In chemistry class, typically we actually use something better called a universal solution, which will actually react to both acid and base. Water, autoionization. Pure water, neutral, that's because it produces equal numbers of hydrogen ions and hydroxide ions, which is the what makes up the water, H2O. So if you combine the hydrogen and hydroxide together, it becomes HOH, 2 hydrogens, 1 oxygen, H2O. HOH is another way to write down the water. And this process is called autoionization. In autoionization, 2 water molecules react to form a hydronium ion, which is H3O2+, and a hydroxide ion. And here is the chemical equation for that. 2 water molecules, when they combine together, one of the hydrogen will be transferred from water to another water molecule, which makes it H3O+ and OH-. If you simplify this, it basically becomes the water will split into hydrogen and hydroxide. Strengths of acid. There are strong acid and called the weak acid. The first of all, strong acids are that ionize completely. It means the hydrogen is going to come off from the anion if the acid is put into the water. And they produce the maximum number of ions, making them a good conductors of electricity. And because this is going to always completely dissociate, this is going to be a one-direction chemical reaction. And these are the 6 examples of a strong acid that you have to memorize. Okay? Weak acids, however, on the other side, they only partially ionize in a solution. So that means they do not produce the maximum amount of hydrogen. They only produce a fewer number of hydrogen ion. And they are not going to be a great conductor as the strong acids. Well, here are some examples of weak acids, but the good news is that you don't have to memorize this. That's because once you memorize these 6 strong acids right here, then you're set. Because we're going to assume everything else besides these 6 strong acids are considered weak acids. So you don't have to memorize these. Just memorize these 6 and that's it. Everything else, assume these are weak acids. Strengths of bases, the same thing. The strong bases will completely ionize and then they produce the metal ions and hydroxide ions. And these are the 6 strong bases that you have to memorize. Because everything else, we are going to basically assume these are the weak bases. You just have to memorize these 6 strong bases and everything else as a weak basis. Just like the weak acids, a weak basis, they only partially ionize so that they only produce a small concentration of a hydroxide ion. And these hydroxide ion and then is considered to be also produce something called conjugate acid. I'm going to come back to this later. All right, strong or weak versus concentrate or dilute. Strong or weak refers to the degree to which the acid and base separate into ions. So strong means they will completely dissociate, and weak means they only partially dissociate. Concentrated or dilute refers to the number of the acid and base molecules dissolved in a volume of a solution, which is basically the concentration measured in molarity. Molarity, we learned in previous chapters, is the measurement to see how something concentrated is. And this can be mathematically calculated by dividing moles of a solute divided by liters of a solution. And when you say concentrated, there's a large amount of moles dissolved in it, and then dilute means a small amount of moles. Remember, these are only a relative terms. Okay, there's no absolute concentrated solution or dilute solution. It's just relative terms. And it is possible to have a dilute solution of strong acid, such as hydrochloric acid, or a concentrated solution of weak acid, such as acetic acid. Here is a dissociation of a strong acid. So take a look at how the strong acids work. So this is going to be before the dissociation. So take a look at here the form that I'm going to be using. It's called HA. H for the hydrogen and A for any kind of anion. It doesn't matter whatever it is. Okay? In the beginning, they're stuck together. Now, after the dissociation and equilibrium, right? Now, what happens is hydrogen and anion is going to get separated. So here is hydrogen that's going to be positively charged, separated from the anion. You note the entire population of HA broke them down into hydrogen anion. How do I know that? Because their concentration level is about the same, right? The length of this bar basically represents the concentration, and all of them will completely dissociate, which is why this is a one-way equilibrium. So, is this reaction reactant favored or product favored? This is going to be product favored because equilibrium is shifted completely to the product side to dissociate every bit of these acids. Now, dissociation of weak acids. So weak acids are assumed to dissociate only slightly, about less than 5% in solution. So let's say that now this time this is going to be a weak acid, HA. And let's say that after the dissociation, this is going to, some of them are going to break them into ions, or we call them dissociate. But you note that only a small portion of them have dissociated into ions. The large portion of the original HA still remains the same, right? If you take a look at these two concentrations, right, only small amount has been, right, only about this much difference has been dissociated into hydrogen and the anion. So based on this, what do we know about dissociation of weak acid in terms of equilibrium? Which side is favored? Reactant side is favored, because a large portion of the original reactant remain as their original form rather than breaking into the product form, which is hydrogens and anions.